Okay, so in this video, I am going to talk about Cramer's rule. So Cramer's rule is just another way to solve the equation AX equals B, where A is a matrix and X and B are vectors. So Cramer's rule essentially says that the ith solution, so xi, is equal to the determinant of AI divided by the determinant of A, where AI, so let's say we have the equations x plus 2y plus 3z equals 7 minus x plus 2y plus z is equal to minus 3 and 4x plus y plus z is equal to 5. So this set of simultaneous equations can be written using matrices as 1, 2, 3, minus 1, 2, 1, 4, 1, 1. So this is the matrix A, and so the first row is just the coefficients of the variables x, y, and z, and the second row is just the coefficients of the variables x, y, and z in the second equation. And then for the third row, we have the coefficients of the x, y, z variables in the third equation. So write this as a 3. And we're going to multiply this by x, y, z. And this has to be equal to the left-hand side, which is 7 minus 3, 5. So we want to find the values of x, y, and z for this set of simultaneous equations. And so this is A, this is x, and put a line underneath just to denote that it's a vector, and this is our B here. And I'm going to write this x, y, z. I'm going to write this as x1, x2, and x3. So y is in essence the second solution, and z is the third solution, and x is the first solution. So now let's carry out Cramer's rule. So Cramer's rule says that x1 is equal to the determinant of a1 divided by the determinant of a. And I'm just going to tell you that the determinant of a for these purposes is minus 16. I'm not going to calculate it on screen. And a1, well, a1 is going to be the matrix A, but the first column of A is swapped out with the vector B. So you can see here, instead of 1 minus 1, 4, for the first column of A1, we'll have 7 minus 3, 5. But then the rest of the matrix will be the same. So we'll have 2, 2, 1, and 3, 1, 1. And so we get that x1 is equal to the determinant of 7, 2, 3, minus 3, 2, 1, 5, 1, 1, divided by the determinant of A, which I'm just going to write 16. And this is equal to, well, I'm not going to calculate it on screen, but take my word for it, the determinant of the matrix is minus 16 as well. So this is going to be equal to minus 16 over minus 16, which is equal to 1. If we now look at x2, so x2 is going to be equal to the determinant of a2 divided by the determinant of a. And if we find a2 first, so this is going to be the matrix A, but the second column this time is swapped out with the vector B. So the first column of A2 will be 1 minus 1, 4. And then the second column will be 7 minus 3, 5, which is the vector B. And then the last column will be exactly the same as the original A matrix, which is 3, 1, 1. So now we can say that x2, which is equal to y, is equal to the determinant of 1 minus 1, 4, 7 minus 3, 5, 3, 1, 1, divided by the determinant of A, which is equal to, we have 16 on the bottom, and the determinant of this matrix here is 48, so we have minus 16. So 48 divided by minus 16, which is minus 3. So we have that y equals minus 3. So finally, x3 is going to be equal to the determinant of A3 divided by the determinant of A. And so A3, that's just going to be equal to, so we'll have 1 minus 1, 4, 2, 2, 1. These are the first two columns of A, but then the third column will be the vector B, which is 7 minus 3, 5. And so x3, which is equal to z, will be equal to the modulus of 1 minus 1, 4, 2, 2, 1, 7 minus 3, 5, divided by the modulus of A. And that's just going to be equal to, so 16 on the, minus 16 on the bottom, then on the top we'll have minus 64, and this is just going to be equal to 4. And so we get in the end that our solution is x equals 1, y equals minus 3, and z equals 4.